All right, so let's look at this little guy. So this is the first of the homework problems. So I'm going to look at a beryllium atom here. And the beryllium atom will have 4 protons, those little blue points. And to balance those out, it's going to have 4 electrons, and those are the little green points. And then it will have 5 neutrons, which are the little gray circles. So that is your standard sort of beryllium atom. Now there are other beryllium atoms, but this is mine. And so what I'd like to do is I'd like to go through and find 4 things. The amount of charge in the nucleus, the amount of positive charge, that is the positive charge from each one of these different protons and neutrons, and then I'll get the negative charge the same way. Then I'll find the net charge on the nucleus, and then I'll find the net charge on the atom, which will include the electrons. So I'm going to find whatever this is. Let's call it Q plus. Then I'll find a Q minus. Then I'll find Q for the nucleus, which will be Q plus minus Q minus, or plus Q minus. And then I'll find the total charge on the atom, which will be Qn minus the charge on the electrons, the nucleus minus the electrons. All right, so that's more or less the plan of attack. How much charge is there on the nucleus? Well, we start with Q plus, that's what we want to find. It's going to be the total charge on each one of these times the number of them. So let's see, that means if I have n protons, and protons will have 2 up quarks, which have a charge of plus 2e, and 1 down quark, excuse me. So I'll need to use the number of up quarks per proton, and then I'll need to find the charge of an up quark and add them together. Then I'll have to add the the number of neutrons times the number of up quarks per neutron. And in that case, that's going to have 1 up quark, and multiply that by the charge of the proton. And we don't have to worry about the downs because those are all negatively charged. So this atom is large enough that its charge varies by the number of its constituents and different kinds of constituents it has. So, although it doesn't really, the nucleus keeps the same number, the same charge, because that's the way we like it. All right, so sort of the way we define it, actually. So let's see, that means we have the number of protons, and we said we had 4 protons, times the number of up quarks per proton, which is 2, times the charge, which is 2/3 e. And then we're going to add in 5 neutrons times 1 up quark per neutron times 2/3 e, which is the same charge. All right, so that means we have 4 times 2 is 8, 8 times 2 is 16 thirds, plus 5 times 1 times 2 is 10 thirds, times e, which is 26 thirds e. Let me think about that for a second. Yeah, it can be off, so that's fine. So that means we've got 26 thirds times E, which is what, 26 thirds times 1.609 times 10 to the minus 19 coulombs, which is equal to, oh, I don't know, 13.945 times 10 to the minus 19 coulombs. And that's sort of what you should put into WebAssign. So for WebAssign, this would be, do I have enough room? 13.945 small e, okay, so we want a lowercase e, minus 19, no spaces there, then there will be a space, and after the space you put the capital C. Okay, that's how you'll put it into WebAssign. Alright, so obviously it's a different element for your WebAssign, but that's what I've got right now. Next, how much negative charge is there in the nucleus? This is the same idea, only instead of the number of up quarks, we have the number of down quarks, and we have the charge for the down quark. So that number flips, right? So over here it was 2 up quarks per proton, now it's going to be 1 down quark per neutron, or 1 down quark per proton and 2 up quarks per neutron, down quarks per, oh, I shouldn't talk, but that's my job. Okay, so let's see, we have 4 times 1 now, because we only have 1 down quark, times now 1/3 E. It's actually minus 1/3 E, but I checked it in WebAssign and the answer is positive. So it's just the amount, it's just the absolute value that you want to put in there. Let's see, and then we have 5 neutrons times 2 down quarks per neutron, and then 1/3 E again. So that means now we have 4 thirds plus 10 thirds E. And you're saying to yourself, you're looking at that and you're saying, how can that be, right? How can that be, right? So we've got 4. Well, obviously these two numbers have to match, because the neutron's going to be electrically neutral. So that's why this guy doesn't change. And then this guy's changed because this guy's got to have a positive charge to it, right? So that this number 16 and this number 4, when you subtract them, that had better be divisible by 3, and it is. It'll be 12. So that actually tells us part C, if we want to know it already. So then we have, well, let's go down here, 14 thirds times that 1.609 times 10 to the minus 19 coulombs. Basically, we've done the same trick. And we then get 5.709 times 10 to the minus 19 coulombs. And you'll have to enter that the same way with the E and all that other stuff. But that is the answer there. Right, it's 7.509 E minus 19 space coulombs. Okay, so there has to be a space between the number and the unit. Remember that. Alright, so now we need the net charge. Well, the net charge is going to be Q equals Q nucleus equals Q plus minus Q minus. And that means we have 13.945 times 10 to the minus 19 coulombs minus 7.509, excuse me, it's a 9, times 10 to the minus 19 coulombs. And you do that, and you get 6.436 times 10 to the minus 19 cool. Okay, so we're doing pretty good. So then we need the net charge, which is Q, which is going to be Q nucleus minus Q electrons. Q nucleus, we just said, was 6.436 times 10 to the minus 19 coulombs, and then we have to subtract Q electrons, which is 4 times E. So we have 4 electrons, so QE is equal to 4E. It's 4 times 1.609 times 10 to the minus 19 coulombs. And let's see, what is that? If we take 4 times 9, that's 36. And 4 times 6 is 24, so there's a 4. So these would all match. Add 4 to this, plus 2, that's 6. So actually that's 0. So it's electrically neutral, right? Which is good because that's what we want our atoms to be, is electrically neutral. And so, bam. Then we're done. So all we did here was we went through each different part of the atom. And actually, I don't need this. Why do I have a second bit there? Well, just repeated that. I did it one at a time. I found out the charge, the positive charge, the negative charge, the nuclear charge, and then the net charge down here. So that's not too much of an issue. Normally, you probably wouldn't do it this way because what would you do? Well, you could figure out the charge on the neutron. We just said the charge on the neutron is 0. So we could find Q nucleus by saying, okay, the charge on any particular proton is E, and then the charge on any particular neutron is 0, so this is 4E. Then we'd have down here just 4E minus 4E equal to 0, because electrons have that minus 1 E charge. So everything works out the same way. Let's see, number 2. Oh, we've got 2 fields. So we've got one field that is pointing eastward. And I'm doing this because that's a way to talk about things, and probably I should have. That still wants to erase? Okay. For some reason, when oh, come on. Okay. All right, so what did I do? So let me pause. Oh, come on, jerk. What is your problem? Okay, I don't think I paused, did I? Okay. Is it still going? It is still going. Oh well. So you got to listen to me yell at this thing. for not doing what I was asking it to do. All right, so let's see. We've got 1,500 newtons per coulomb eastward, and then I have 2,000 newtons per coulomb south, and I only did that because this is perpendicular. And I don't want to press that. I do want to press that again. But what we want to find out is the field produced by the combination, which is this, right? So we've got two uniform fields, and we want to find out the total field here. Okay, so that seems pretty reasonable to me. And the way we do this is because it adds vectorially. We add 1,500 newtons per coulomb squared plus 2,000 newtons per coulomb squared. And that's all we really need to do. They have a common factor, these guys, of 1,500 or 500 newtons per coulomb. So that means we have 3 squared plus 4 squared, which may have been the reason why I did this, because that means I have 500 newtons per coulomb times the square root of 3 squared plus 4 squared. That's one of those wonderful magic triangles that we know, which is 5, right? 3 squared plus 4 squared equals 5 squared. And the square root of 5 squared is 5. And we do 5 times 500, and that's 500 newtons per coulomb. And that is part A. Part B is what happens now if you put a field, or put a charge on that, charge in that spot. So we've got our field going this way, right? And we put a charge here. It's going to feel a force going this way, same direction. So that force is going to be equal to the charge times the electric field, which is 500 times 10 to the minus 6 coulombs. Mu is micro. Micro means 10 to the minus 6. And then we multiply by E, which is 2,500 newtons per coulomb. Obviously, the coulombs cancel. I can turn this to 2.5 and get rid of 3 of those. And I can also put this to 0.5 and get rid of 3 of those. So now we're at 2.5 times 0.5, right? Newtons. That's 1/2 of 2.5, so that'll be 1.25 newtons per coulomb. Bang. Okay, and that's actually what you want to do with fields. If you want to find the force from two things that are producing fields, first you have to figure out what the net field is, and then just multiply it by the charge, and you're done. Okay, so that's basically how you do that. Shouldn't be too much of an issue. Ooh, a long stick. So this is a tough one because it does something weird. I like the weird thing that it does, but it's kind of a little weirder than it needs to be, I think. I don't think I added. I think you only have to do B, C, and D. I want to do A because it makes life easier. So A is just finding the net charge on this thing, and then eventually we'll find the force from the charge. We'll find the polarization. That's the tricky part, and then we'll find the torque from the polarization. So let's see. We just want to find this sort of net charge. That means we have 20 microcoulombs minus. Why I did that, I don't know. 4 microcoulombs, which is 16 microcoulombs. Be a big C per coulomb. So 16 microcoulombs is the net charge on this thing, and that's what it's going to respond as far as the force is concerned. So the force, you can do it two ways. Either you can find the force on this and the force on that, and then add them together, or you can, after you've found the net charge, just multiply by the field, which is 1,000 newtons per coulomb. So we have 16 microcoulombs times 1,000 newtons per coulomb. Get rid of those. This is actually 10 to the minus 3. This is 10 to the minus, or 10 to the third. This is 10 to the minus 6. So that gives us 16 times 10 to the minus 3 newtons, or 16 millinewtons. So not a lot of force on this guy right here. Okay. Polarization. So the polarization is a little bit odd. So remember, if we had these two have the same charge, right, the polarization would be P equals QD, where D would be this distance. Now, in this case, we have different Q's, right? So what we'll have to do is we'll have to somehow figure out what would give us this. Now, the actual way to do this is to go through and do a derivation using the torque itself to figure out how to do it. I had to do that to be sure that what I was doing was right. But my impulse was right in the first place when I looked at this, and it's just going to be P is equal to Q1 minus Q2 over 2 times D. So let's look at that really quick here, or here, right? If we just have the same charge, then you'd have Q plus minus Q, because it's a dipole, so this has to be one of these has to have a larger charge than the other one. Divide by 2, then multiply by D, which is just QD, which is the same thing. So it at least gives us that in the limit. And like I said, if you wanted to go through and use the torque to figure out what that was, you'd get the same answer. So now what do we do? Well, we add these two things together, right? Or we subtract them, basically. So we have 20 microcoulombs minus 4 microcoulombs over 2 times 5 over 100 meters, 5 centimeters. Probably should have just left centimeters because I have to do the same thing with the coulombs. So that means I have 20 minus 4, which is 24 over 2, which is 12 times 10 to the minus 6 coulombs, times 5 times 10 to the minus 2 meters, which is 60 times 10 to the minus 8, or yeah, 60 times 10 to the minus 8, which is 6 times 10 to the minus 7 coulomb meters. The way to write that would be, if you were really weird, microcoulomb centimeters. So that's more or less the answer. So that would be like 6e minus, that's a little e, 7c space c times, it'll be the little asterisk, m. And that would be the correct answer in WebAssign. All right? And then we want to find the torque from this configuration. And torque then is N equals PE. So instead of QE for the force, the torque is PE. Actually, it's PE sine theta. And this is theta. So this is perpendicular. So theta equals 90 degrees. Another way to say that is this is perpendicular, so the sine is 1, not 0, 1. And so our torque is then just 6 times 10 to the minus 7 coulomb meters times 1,000, 10 to the cubed, 1,000 here, newtons per coulomb. So those coulombs cancel. And we have 6 times 10 to the minus 4 Newton meters, which is good because Newton meters are what we measure torque in. If you'll remember that from oh so long ago. All right, so that's more or less how that's done. So I keep wanting to, and I always forget to do it until it's too late. I keep wanting to add this into this problem, and that's just because we want to do. It shows very clearly that with the charge and the force, you're doing the same thing as with the polarization and the torque, right? You find the charge, and you use that charge to find the force, and here you find the polarization, and you use that polarization to find the torque, and the only sort of difference here is that you have that sine theta in there. That is, if the dipole was aligned with the field, it wouldn't feel any torque. So the torque changes as this rotates, but it's going to induce a rotation, right? The field is going to induce a rotation. It's pulling this guy this way, and it's pushing this guy that way. And it's going to pull the entire thing this way because it's unbalanced. But if it was balanced, it would just sort of spin around in a circle. No, it wouldn't spin around in a circle. It would go back and forth and back and forth and back and forth and back and forth, unless it had an initial velocity. So that looks like a no. It should not look like a no. Oh well. So that's basically what the point of that problem is. Okay. Last problem on the homework is a conservation of energy problem, basically. So I've got 3 things. I need the electrostatic potential at the turning radius. So basically, we're firing this proton at this nucleus. It's going to come over here, and it's going to sort of come back. Seems reasonable. That's what happens to things. Because this is positively charged, and this is massively positively charged. I think it's 20 E for me. And it stops about 900 nanometers away, and it then goes back to wherever it came from. So when it's very far away, it has some speed v, and that's what we really want to find. But we're going to use the electric potential and the electric potential energy to help us find that with conservation of energy. So eventually we'll get here to 1/2 mv squared. This thing has to be equal to the potential energy there, which is QV. And V, you'll remember, is equal to KE times Q over R. R is basically the distance from here to here, and this sort of misrepresents the size of the nucleus. This guy is actually about femtometer size, let's say. And this is nanometer size, so it's like, they're not about the same size. This thing's about 1 million times smaller than it's depicted here. So, and this is actually much larger than the atom itself, so it doesn't get anywhere close to the nucleus before it turns back. All right, so it's actually going to be, that makes it even more interesting that it doesn't get anywhere close and how fast it's going to be moving, to be honest. So this Q here is the potential from this guy here. That's a big Q. This little Q here is the Q over here. It's the plus E. So we want to use the big Q for the potential, because that's the thing that's saying static, right? And we're doing electrostatic, so potentials come from static stuff, and dynamic things don't give you the potential. So I shouldn't say that. But it's good enough for us. We're not going to do anything where we have to worry about that. So KE was 9 times 10 to the 9 newtons meters squared per coulomb squared. Q we said was 20E. And R we said was 900 nanometers. Okay, so that's... we can cancel out some 9s. That's good. So that means we have 2 times 10 to the 9th, that guy. Then we have 20 there, so we add 1. The 2 came out here. Then we have let's see, what is this? Why did I get lost? Okay, 20E. We're going to have to deal with the E later. We had the 9. Okay, so then minus 9 here, but that comes up because it's in the denominator, so that's plus 9. And then we have 100, so that's minus 2, times 1.609, that's the E, times 10 to the minus 19 coulombs, which we seem to have used a lot. So that's like 3.22 times, this is... see, 18 minus plus 1 is 19, minus 2 is 19, right? 9, 1, 19 minus 2 is 17 minus 19, which is 32, 10 to the minus 2, so it's 32.2. I forgot my unit somewhere. Oh, crap. That should be millivolts. Okay, 32.2 millivolts. Okay, I wasn't crazy. All right. I thought it was crazy for a little while, but I'll be okay. So we want to find the total energy of the proton. Well, the thing is it's the same everywhere, right? It's the same number here as it is right here, and we have the information to figure it out right here. So the energy is just the electrostatic potential energy at this point, which is Q times V, which we kind of showed earlier. So that's 1.609 times 10 to the minus 19 times 32.2, that's coulombs, times 10 to the minus 3 volts. And then you just have to do it, right? Put it in your calculator and have some fun. And you have 5.18 times 10 to the minus 21 joules. And so that's our total energy. And remember, our total energy is equal to 1/2 mv squared, which is also equal to this guy here, which is 5.18 times 10 to the minus 21 joules. Okay, so that doesn't look very good, except when you go out and you say, okay, well, what does that proton weigh? What is the mass of the proton? It's 1.672 times 10 to the minus 27, excuse me, kilograms. And then we still have a v squared that's equal to 5.18 times 10 to the minus 21 joules. 21. It's running away from me. And it's literally the tablet is running away from me right now. Let me see. So I multiplied this 2 over here, this thing by 2, that's 10.36 instead. So then I divide by this 1.762, so we have 10.36 over 1.672 times, this is 10 to the 21, minus 21, plus 27 joules per kilogram. That actually looks pretty familiar. So that ends up with a 6.196. 27 minus 21 is 10 to the 6th. Joules per kilogram, remember, is meters squared per second squared. So when we take the square root, let's see, what's the square root of 6.196? It is a well-known quantity, obviously, which is 2.489 times 10 cubed meters per second. And that's the initial velocity of this guy here. And that's basically the procedure if you need to find something with conservation of energy in the electrostatic sense. You're going to want to find the potential and use that to find the electrostatic potential energy, and then use that in conservation of energy, more or less. All right. So that is the homework. You follow these procedures and you will be happy and life will be good. All right. Bye now.